Okay. Hey everyone, welcome. My name is Octavia, or VVX7, or VV, or sometimes V. Um, and thank you all for coming out to watch this. So I'm a principal security engineer here at Prelude, and you're joining us in our weekly Discord sessions where we invite a guest speaker to come out and talk about something cool. And the basic format we're looking to do is to have people, either experts in their field or people that are just getting started and looking to do the first talk, come out, do a thing, get some mentorship if that's what they need, and have fun. That's what we're aiming for. So this week, really fun talk. We have Frank, who will be speaking about building a Windows Packer. I've been looking forward to this talk for weeks. I'm super excited. Yeah, so with that, I will hand it over to you.
Yeah, so I go by Frank 2 or Amethyst or varying words that signify purple. I mostly go by Frank 2 in the hacker community. I've done a lot of stuff related to malware. I've written executable parsers and things like that. But we don't have a lot of time. I'm not gonna wallow in an introduction. So let's just get started. So, what is a packer? A packer is basically an executable compression tool that's primarily used for a few things. It's used for compression, obviously. It's also used for obfuscation and evasion. A good example of a compressing packer is you may have heard of it. It's called UPX. An obfuscating packer is called Pacman. It's used by I can't remember which company it was. I believe it was Riot Games that created Pac-Man. They use it for League of Legends and Valorant. It's I've had to tackle that packer before. It's really annoying to deal with. It's also used for evasion. You may have heard of the smoke loader variant of a malware family. There's a lot of really good packer things in there if you're a reverse engineer and you want to see some like extra cool tricks that you could possibly do for your packer. I'd highly suggest looking at smoke loader for that. But fundamentally, a packer is actually really simple. It only has a few main steps. It compresses an executable image, it decompresses that image at runtime, it loads that image in accordance with the platform's executable loader, and it executes that image. It's very basic stuff, basically, when it really comes down to it. And what is also simple is what a packer consists of. There's two main pieces that you have with the packer. There's the actual packer, which actually creates the packed executable for you, and the stub, which is the actual packed executable, which contains the compressed executable data. So here's what I'm trying to teach with this presentation. I want to build an automated build system for creating a packer because a packer is actually a complex little piece of software. And creating a build system that actually manages the various pieces, like the putting the stub into the packer and actually being able to test the packer, is actually really useful. I'm also going to be going over how to actually manipulate a Windows executable. Usually, you use the Windows executable format to analyze. I'm going to be actually covering how to actually manipulate that Windows executable, and I'm also going to be showing how to mimic a minimal amount of the executable loader for Windows and how to process and load an arbitrary binary. Um, this Packer presentation is going to cover the basics of Packers, so you can also do this on Linux, but it's going to primarily focus on Windows. So you're going to need the following things. You need a little bit of knowledge of C++, a copy of Visual Studio with C++ installed, and a copy of CMake. You can get the source code for this tutorial on GitHub. I highly recommend grabbing it because it's a much more detailed tutorial on how to do this. And there's also source code for you to actually like fork and actually build your own packer. It's actually a really good project, I feel. So let's start with CMake. We need the following CMake projects. We need a project for the packer, we need a project for the stub, and we need a project for the dummy. The dummy is basically what we're going to actually test our packer on. It's going to basically be a simple thing that prints a simple message, and that's all we're going to deal with. It has the C++ runtime, and we'll know if it executes properly because it exits with 0. We also need a copy of zlib, a compression library, to actually compress our target executable and put it in the packer.
Hey,
So
Frank.
this is what our layout is going to look like.
I just want to interrupt you for a
Yeah.
second. Sorry. I want to make sure your screen's not frozen and that we're seeing what you're seeing. So I'm looking at like your PowerPoint window and you're on slide 3. Is that correct? Or
No, I'm not on slide 3 actually.
Okay, so I think maybe your video is borked. Do you want to stop
Okay,
share?
should I reshare?
Yeah, just reshare again. Yeah, please.
Okay. Here, I'll try sharing the whole screen instead of just the program.
Cool.
Okay, so basically, this is what the directory layout is going to look like. In every project that we're going to have, this is basically going to produce. It looks like, let's see, it's going to produce four executables. It's going to produce a library for zlib. It's going to produce our packer. It's going to produce our stub, and it's going to produce our dummy. cmakelist.txt is basically the make file for cmake, and it contains all of our metadata. So we have a dependency chain that CMake will handle nicely. The packer and the stub depend on zlib. The packer depends on the stub, and the dummy depends on the packer because obviously the dummy needs to be packed by the packer. Our packer CMake project will be our example for CMake today. In cmakelist.txt, we need to declare a version of CMake we want to support in the Packer project itself. This is accomplished by the CMake minimum required function in CMake. As you can see here, we're targeting the most recent version, 3.24, but it doesn't need to be the most recent version. You can actually target lower versions. And then we actually declare our project with the project keyword. We've declared it as a C++ project just to make sure that it doesn't get confused by the C project that is zlib. And it uses CXX for that keyword. We also want to remove DLL runtime dependencies. This basically prevents us from actually using the DLL runtime that comes with Visual Studio and actually makes it so that everything is compiled statically. The angle brackets are a CMake generator expression that emits debug when in debug mode and nothing otherwise. If you want to read more, if you want to learn more about it, you can look at the GitHub repo. Which, by the way, I'll probably drop in the chat because we'll probably drop it in the YouTube video too because we were having slide issues earlier. Um, yeah. Okay. Next, we need to collect our source and resource script files. This is actually really easy to accomplish. With the file keyword, we can use a global recurse function to iterate over a certain file type in a directory. Here, I'm just iterating over the source directory, so it's really simplified. There are also some what are called resource script files in Windows. We'll cover resources in a minute, but this is basically how to collect everything. The source group keyword is actually really helpful if you're familiar with Visual Studio. It actually creates a little source group to collect various files. You may have seen this in your C files or header files in Visual Studio. It usually creates this for you, but because we're instrumenting Visual Studio, we have to add it ourselves. Then we add our sub projects. These are the directories that contain the other CMake files. We just add the subdirectories, and then we recall their inner projects later. You'll see me referring to the zlib static library, I think, in the next slide. I'm not sure. It might be a slide after. Yeah. Okay. No, it is. It is. It is after this, I think. So you can actually use CMake to generate files for us. This is actually really handy for being able to store our stub executable into our binary because it actually resolves the location on disk during the build step. So this way, you can actually have our resource directory include the target file of the actual build, since CMake is actually doing the build chain for us. So with this, we can generate some resource script files and some header files to eventually include. So then we declare our Packer executable and include our third-party dependencies. We use the add executable function to add the header files and the source files. And I can't remember exactly why this is, but to include resource files, we can add the target sources to the Packer project, and then they get included that way. I can't recall why that was done specifically. And then we add our third party dependencies with target link libraries, which basically is a way to actually link the actual compiled project of the library. So we need to make our binaries aware of our import directories. For the Packer, we're using generated files to eventually be included in the project, and so does zlib. So we need to actually include the uh, the generated files which are stored in the binary project or in the build directory at build time, and then we include that in our projects. For the stub, we're resolving zlib. we're resolving zlib includes in this CMake file because there's a requirement by CMake for a dependency to be accessible from the same directory as the project. So we need to include it in a kind of weird way, but it works. So I'm happy with that. It resides outside the stub directory because of that. So target include directories is the function you're looking for, and this is basically what our includes look like. We include the source directory, which has our headers. If we have any, there's only really a main CPP file in the example, but in case there are headers, we put our headers there. In the build directory, in the with the config variable, which would be debug or release, depending on which you configured your build with, and then the zlib directory for the actual source, and then the build directory of zlib for the generated CMake for the generated headers that zlib creates when it builds. Then for the stub project, we also include the zlib directories so that the stub is aware of zlib. Finally, we declare our dependencies. We add the dependencies for the packer, which is the stub, and we add the dependency for the dummy, which is the packer. This way the build order is basically stub packer dummy in a CMake. And then the really cool part about this process, I feel like, is being able to actually test the packer. So there's a lot of problems when it comes to packing stuff, and it's really good to have a way to actually test things when you're done. When you're done building. So we have a very simple command. We run the packer with the dummy file, and then it compresses and packs the dummy file, and then we actually test the packed executable. In our example, we just output to packed.exe to produce the packed executable. In an ideal environment, you would have argument parsing and things like that, maybe a cool UI to actually do the packing for you, and you would actually have something to save it to a proper file on disk. But for our example, we're just outputting to the pack.exe. The stub and the stub and the dummy CMake file should be easy to understand now, and you can see that in the GitHub repo for those files. We now have a CMake project that does the following. It manages our various dependencies and builds them in the right order. It builds the stub binary and adds it to our packer binary automatically for us. And it unit tests our packer on a binary and verifies its unpack routine functions. So you can see how all this works by basically issuing the following commands in CMake. You make a build directory, you cd to that directory, and then you call CMake on the previous directory, which usually contains a CMake file. Then you call CMake build, and you with the config release, this is for Windows. On on Linux, you actually have to pass a like an environment variable to do release builds, but yeah. And to do the test, we just run ctest and with the release config, and then on packed, it produces the string if all went well, and it exits with code 0. So that's basically how you know that the packed executable ran, and that's how the ctest works too. We now have to add an arbitrary executable to our stub. Sorry. Oh no. Oh god. Sorry, my mouse went off the rails. There we go. We now have to add an arbitrary executable to our stub binary. What the stub does right now isn't really relevant. We just need to worry about the vectors by which the binary eventually gets delivered into the stub. We just need to worry about getting the binary into the stub. We can worry about the stub in a minute. For the packer, our chosen vector is a feature of the Windows executable called the resource directory. This contains arbitrary file data such as icons and bitmaps for use within an executable. There's also the config file. There's also basically a bunch of various strings in the resource directory. But for our purposes, it contains our sub binary. Accessing resources is really simple. You find the resource handle given an ID and a type string. In our case, it's the IDB stub that we declared in our header, in our generated header, and the string stub. Get the resource size and load the given get the resource size and load the given resource handle and lock the byte pointer for the resource data. It's better to be explained in code. So here's that code. So we use the find resource a function with a name and a type. In our case, we've converted the header ID to a string, and the type is just basically a substring. And if it returns null, that's an error. That basically means you couldn't find your resource. After that, you get the size of the resource with the module handle for the current process. This function actually comes in really handy later in our stub binary. We'll get to that. We'll get to that later. You'll see it again. That basically gets a handle to our current executable, and we get the resource that we found, and then we load the resource. I'm not sure why they separated load resource and lock resource. It's kind of confusing, but you have to load it before you lock it. And locking the resource actually gives you the actual binary data. Windows executable starts with what's called the DOS header, or how it's referred to in the Windows API, the image DOS header. That's actually the name of the structure. It's a large structure, but we're only concerned about two members because the other members are only relative to actual DOS executables, like really old executables. We're concerned with eMagic and ELFA new. eMagic is the magic value that signifies the DOS header, which is 0x5A4D or MZ in ASCII. It stands for, I can't remember what it stands for. It's like it's Zbikowski and something else. I think Mark Zbikowski is the name. Yeah, I think it's Mark Zbikowski. Okay, ELFA new is the offset into the image that contains the NT headers, which contains most of the metadata needed for our executable. So here's how you get the DOS header. It's really simple. The DOS header is just basically at the very beginning of the executable. So our target data is I can't remember if target actually contains. Yeah, the target I believe contains our yeah, our target binary. Exactly. It's the binary we're trying to pack. And you get the DOS header at the very header of that. And then you basically get the NT headers, the actual PE headers for the executable by just adding ELFA new to the base of the target data. And you also verify that the signature is correct with 4550 or PE for short for ASCII. But for our example, we're only supporting 64-bit executables because we're simplifying things. And 32-bit and 64-bit executables contain actual different challenges. I find that 32-bit executables are relatively more challenging due to a few various reasons. So we're only covering 64-bit executables today. The NT headers are also rather large and detailed, so we'll just be covering a minimum amount of variables needed for our packer. As you can see, the magic header and the optional header of the NT headers contains a magic header signifying that this is a 64-bit executable. After the headers, a PE is organized into what are called sections, really easy to understand. These sections contain program data such as executable code as well as plain old data. So things like the resource directory, things like the import directory, uh, things like um, things like executable code, things like other various uninitialized data that like the uninitialized data that gets initialized at runtime. We're going to insert an arbitrary section into our stub data containing our compressed executable to later retrieve and load it at runtime. You'll see why this is so easy in a second. We compress our data with zlib's compress function. It's a really simple function. We then align our stub buffer size data to the image header's file alignment value and append our compressed data. So an address or file or value is aligned if it is evenly divisible by a certain value. Basically, various things need to be on certain boundaries within addresses, and they usually align to certain values, usually 0x1000 for memory and 0x400 for disk. I can't recall the reason for this, but yeah, it's something to keep in mind for later. So here's how we actually get our stub data. We load the resource, and we get a vector to we get a byte vector to the actual stub resource. We then get the DOS header of the actual stub data, and we store ELFA new for later because we're going to be restoring the headers later on when we resize the buffer. Because when you resize a vector, sometimes the base address changes, so sometimes you need to get the headers again. It's a little annoying, but it's the unfortunate reality of resizing vectors. So we get our NT headers by adding ELFA new to the stub data's base. Then we get the file alignment and the section alignment. We'll talk about why file alignment and section alignment need to be differentiated. Well, actually, I'll talk about it right now. Basically, we'll explain it a little more later. But there are basically two memory types for an image for an executable image. There's the disk image and the memory image. It actually looks different in memory than it does look on disk. That's the reason for the two different variable types. Then we check if our stub data is actually aligned to file alignment for our next section. And if it's not, we resize it to the aligned boundary. The align function down there basically takes the value, and if it's not aligned, it aligns it to the given alignment. So then we get our raw offset to the actual stub data. Now that we know we have an aligned section, that we're going to add data to. We add the size of our packed binary to the stub data. This is our compressed binary, I believe. And then we add we add the unpack size because we need to pass that value to the decompression. To create a buffer that's actually we need to create we need to create the unpacked buffer at the stub's runtime, and we need to know the size of that buffer. And unfortunately, zlib does not provide that to us, so we need to encode that byte buffer. We need to encode that size in the actual section. So that precedes the actual pack data. Then we add the pack data to the actual stub data, and that gives us our packed section. So we have our pack data there, but the metadata is not aware of it yet. We start by incrementing the actual number of sections present in the file header of the NT headers. That's simple enough. We basically just increment the number of sections variable within the file header of the NT headers. Then we acquire the section table, which is actually a little more complicated than you would think. The section table directly follows the optional header and the NT headers, but don't be fooled. The section header actually follows it after the size of optional header variable in the file header, which is really confusing because it looks like it directly follows it, but it actually follows directly after what it believes is the size of the optional header. If you think a little bit, you can actually realize you can put the optional header way past where it's actually supposed to be with the greater size of optional header. There are actually examples of this, and it actually fools some parsers because they always expect it to be directly after all the other section headers, and it's actually not there. So make sure you actually add the size of optional header to the base of the optional header, and to get the actual offset to the section table. So in the section table, we're only concerned with the following variable names: the name, which is literally the name of the section. It's an 8-byte name. The virtual size, which is the size of the section in memory. The virtual address, which is the offset in memory. The size of raw data, which is the size of the section on disk. The pointer to raw data, which is the address to the section on disk, and the variable characteristics, which is basically information such as whether or not the section is executable, whether or not the section is initialized or not, that sort of thing. So a Windows executable has two memory states: a disk state and a memory state. I covered this earlier. These states have entirely different memory layouts, which is why it's important that you know the difference between them. People get tripped up on what an RVA is. It's really just a memory offset. That's all it is. It's an offset into the memory image. Virtual address and virtual size correspond to those states in memory. Virtual address is a memory offset, also known as a relative virtual address, or RVA. A lot of people get confused between a disk offset and a memory offset. Just recall that those two things are very different. The memory layout is very different from the disk layout. And that's why pointer to raw data and size of raw data point at the disk. Characteristics represent various information about the section, such as whether or not it's executable, or if it's initialized data. When adding our compressed data, we save the disk of the offset to our data for the purpose of adding it to the section table later. With an alignment function, we can easily calculate our new section's memory offset in accordance with the image's memory alignment. The alignment function essentially calculates the difference between the aligned value and the current value, then adds that difference to align the value. It's very simple. You can see it in the code on the Git repo once I link it. As for characteristics, we simply need to mark the section as being readable and initialized. So here's what basically adding that section metadata looks like. We get a pointer to our section, which is basically the section index we got earlier. Then we get the previous section. We get a pointer to the previous section. We get the virtual offset with the aligned value of the virtual address plus the virtual size of the previous section. We get the virtual size, which is actually just the size of the section data. For some reason, compilers like to use the virtual size as the size of the section on disk, as opposed to what it looks like on in the actual disk data. But I'm not sure why they do it this way. But that's the precedent, and I'm using it. The raw size corresponds to what the section size looks like file aligned. So we align that section size to the file alignment, and set that as our raw size. I don't know why the raw size is different that way, but it is. So then we assign basically the name of the section. I like to go with .packed. If you want to do something a little less obvious, like R data or something else like that, you can. If you want to you add the virtual size, you add the virtual offset, you add the raw size and the raw offset to the section, and then you mark the section. You mark our section as initialized readable data, which is basically there's a whole lot of if you look at the documentation for image section header, you can see all of the different variables that you can add for your section. Yeah, it's listed in the README. There's a lot of links to the documentation in the actual Git repo README. Unfortunately, now that we've added this section, we've increased the size of the image. But we need to actually make the image aware of the fact that the size has been adjusted, because the size of the image is actually encoded within the PE file itself. So you simply adjust the image size variable in the optional header to fix it. You basically use the alignment function to take the virtual offset and the virtual size of the last section and align it to the section alignment, and that's basically the size of your image. Now you have a stub buffer. Now you've basically encoded your buffer, your packed binary into your packed stub. So how do we unpack that stuff? The unpacking process as an abstract is actually really simple, just like a lot of other things. You decompress the target binary, you simulate the loader as much as you like, you call the entry point of the original image. Obviously, the second step is the most complex, and it's mostly what we're going to be covering. So, as a bare minimum, to load our dummy binary, we need to do two things. We need to resolve the DLL imports, and we need to relocate the execution data to point at our loaded memory. So we can then proceed to get our entry point, traditionally called the original entry point, or OEP for actual packed binaries, out of the headers and call it. In total, this actually produces a very simple main routine. So here's what that main routine looks like. At the top of the image, we actually get our packed image from the section data. Then we load that image. Then we actually load the imports, the DLL imports. Then we relocate the image. Then we get the entry point of the image and call it. It's actually very simple. We can access our executable headers at runtime with the Git module handle at API function. This is what I mentioned earlier with the when getting resources. From there, retrieving our compressed binary from the stub is as simple as parsing out the section we added, then doing some pointer arithmetic to retrieve it, and finally decompressing the data stream. So this is what that looks like. We get our image base by calling git module handle a and converting it into a byte buffer. This makes pointer arithmetic really simple. Then we get the actual NT header from the headers, if you'll recall from before what that looked like. Then we get the section table with the convoluted way to get it. I really hate the section table. It's really annoying. Then we get our packed section by just iterating over the section table and looking for a section that starts with .packed. And if it's not there, well, then there's an error, and that's another error for our tests. So then we actually we decompress our packed image. First, we get the section start by getting the actual base plus the virtual address. Then we get the section end by calculating the section start plus the virtual size, because that actually contains what the actual size of that data is. Then we get the unpacked size by getting the first 64-bit value out of the section, which is what we encoded as our unpacked size. Then we get our packed data from the section start by actually advancing past that pointer, past the previous 64-bit value. Then we get the packed size by calculating the virtual size minus the size of the 64-bit value. Then we get the decompressed. Then we get the what is that? We get the decompressed. We get the what am I doing there? I'm sorry. Oh, I'm not sure what I'm doing there. I'm sorry. I'm wasting time. So we get the decompressed size. We cast it back to a Yulong. Well, basically, we're uncompressing. We're uncompressing our data at this point. Um, oh, the decompressed value. It's a vector. It's okay. I'm sorry. We're allocating our vector. We're allocating our unpacked vector to actually put into to actually decompress our data and then actually returning the decompressed data. I'm sorry. I had a brain fart. So remember disk and memory addresses? We need to convert our disk image to a memory image. We start with a call to virtual alloc with the image size value from our headers, noting that the new memory page should be executable. We then map our section data via their virtual address offsets onto that new memory section. In our example, we also copy the PE headers. You can choose not to make it a little more obfuscated, but it'll make it a little thing. It'll make things a little bit harder for you. You'll have to implement a lot more things. So here we get the actual NT headers, and then we get the section headers, and we get the size of the image, and we allocate it. Virtual alloc is going to come up a lot when it comes to actually allocating executable pages. It's the only way to actually allocate executable pages on Windows. If there's another way to actually allocate executable pages on Windows, I'm not sure. And maybe you'd be able to do it with malloc and actually calling the virtual protect functions to do it. But virtual alloc is how to allocate executable pages on Windows. So then you use the size of image value, and you use the size of image value from the NT headers, and you add the you make the page executable read write with the page executable read write variable, and we convert that to another byte buffer for more added ease of use with pointer arithmetic. So then we actually copy our actual section data, and that's actually very simple. So for every section that we have, if the size of raw data is greater than 0, because sometimes you could just have a virtual section that doesn't actually have any raw data in it. So we make sure of that, and then we copy our section with a little bit of arithmetic. So the base plus the virtual address, remember the virtual address corresponds to the memory address of our section. This is our target this is our target memory image. Then we get the actual image data at the pointer to raw data because that's our disk image. And then we copy that data with the size of the raw data. So yeah, if that's basically how you copy all of the different sections into the new virtual image. Certain PE data structures are stored in what's called the data directory. These directories are what we'll parse out parse out our imports and relocations. We get a directory-specific data structure by parsing at the virtual address of the given data directory. The data directory is stored in the optional header of the NT headers. It's basically at the bottom. And sometimes because of the size of optional header, these directories aren't there. That's why the size of optional header is there. I don't know why they didn't use just a variadic struct, but that's what they did. So here's how you get the actual import descriptor as a result. You get the NT headers from the image, you get the data directory from the optional header, and you get the import directory with the image directory entry import defined. And then you get the import table, which is just an array of import descriptors. So the import directory consists of an array of import descriptors, like I just said. These import descriptors contain an address to the string of the DLL to import, as well as their API entries. And an import descriptor is an import table. These are functions to import, and an address table, functions which have had their address resolved. Though the names are confusing, these correspond to the original first thunk, the import table, and the first thunk, the address table, within the import descriptor. So this is the imports and exports rely on what are called thunks. These are just basically addresses which could represent a number of object types. For our imports, we'll only ever have to encounter an ordinal and an address of data thunk. An ordinal is a value with a flagged most significant bit for differentiation and an index value into the DLL's export table. This is essentially a lookup by index rather than an API name. An address of data thunk points at this data structure, which is an import by name. I don't remember what the hints for. It might be related to um, the actual index, but I can't recall. And then the actual name, which is a variadic C string, which makes the structure a variadic struct, and makes it so that it can be actually varying sizes within the actual PE file. The import descriptor array is null terminated like a string, which can provide problems. The import table and address table are also null terminated. They are also mirrored, as in the import table thunk0 goes into address table thunk0 when it gets resolved. To resolve the imports for the address table, we use the function load library a to load the given DLL in the descriptor and get proc address for both the ordinal and the import by name structure. When simplified, this is what our import table looks like. For every import descriptor, you load the DLL, you parse the original and first thunk, and for every thunk within the original thunk, if the ordinal bit is set, you import it by the ordinal, and for everything else, you import by name. So then you store the import in the first thunk. And you repeat this process for every DLL that gets imported and every basically function that gets imported in those DLLs. So this is what our loop actually winds up looking like. As you can see, at the top of the loop, we make sure that we're iterating over the loop, and we haven't reached the end of the loop by verifying that the original first thunk is not 0, because otherwise it's an address to our various thunks. Then we get the DLL name, which is basically which is the name function within the DLL, is actually not as just a pointer to a C string. It's an RVA pointer to a C string, I should add. And we load the DLL with our import. We just basically call load library on that DLL name. If it returns null, that's an error. Then we get the lookup table, which is the original first thunk, which is another RVA, and then the address table, which is the first thunk, which is another RVA. You'll get used to RVAs. You'll get used to seeing RVA. Wait, I went too far. Okay. Then we actually have to iterate over the lookup table. So we start by actually checking whether or not the lookup table is null. The address of data within the lookup table is null. And then we declare our function variable. Get proc address returns far proc, which is just basically fundamentally a function pointer. And then we get our lookup address, which can be basically an ordinal, or it can be an address of the import by name. If the lookup address has an ordinal, we do some pointer. We basically recast our ordinal with the mask of the lower 32 bits of the ordinal index, and get proc address actually handles the importation of that for us. If get proc address returns a null pointer, that means there was an error, and you can actually get that error by calling get last error if you need to. Otherwise, it's an import by name if it's not an ordinal, and then from there, basically, we just import the name. We just basically get the import by name structure, and then we call the import by name within the DLL import. Then we actually store the function within the address table with basically a 64-bit value, because we're on a 64-bit executable. Then we advance the lookup table and address table, and then we advance the import table too for the next DLL. Okay, I need some more water. Give me just a moment. So, okay. Addresses for a binary are usually hard-coded to point at an original image base. This is what the relocation directory aims to fix when a dynamically allocated base is involved. A dynamic base for a binary is also known as address space layout randomization, or ASLR. You might be used to that if you've done exploitation development. This is an optional characteristic for a binary that may or may not be present. For our example, it is. For CFF Explorer, it's not. If you're trying to pack that binary, that's a good test binary to use. We can check for the presence of a dynamic base by checking the DLL characteristics variable of the optional header. So that's what this looks like. You get the NT headers, and you check the optional header DLL characteristics for the image DLL characteristics dynamic base. That tells you whether or not there's a relocation. For us, this is an error because we actually have to relocate our image because there's a very specific way to actually load a non-relocatable image, which we're not supporting for this example. And if the actual address of the import of the relocation directory is null too, that's an error as well. So while relocations for 32-bit binaries gets complicated, 64-bit is actually really simple. For every relocation, you add the base delta. The harder part is actually parsing the relocation data. So calculating the base delta is simple. You subtract the image base header, and the optional header from the allocated image base. So we convert our virtually allocated image to a uint pointer, which is guaranteed to contain which is guaranteed to be a size of that can hold a pointer, and we subtract our image base from that value, and that basically gives us the difference between the target base and the encoded base of the actual binary. So this is a relocation directory header. This is another null terminated array. The virtual address points to the base address to relocate. You'll see you'll see offsets within this directory. Offsets to offsets from the virtual address within this relocation to the target to relocate. It's a little confusing, and you'll see that it's a little confusing. I'll try to explain it as best I can. The virtual address points to the base address to relocate. The size of the block is the size of the entire relocation entry, header and all. Type offset is an array of encoded offsets from the virtual address base to relocate. While it's commented out, it does actually reside after the size of block variable. We'll need to do some pointer math to actually get to it. Type offset encodes 16-bit values in the following way. The top 4 bits with a mask of 0xF000, so it's like the 4 most significant bits, if that makes more sense to you, contain the relocation type. The lower 12 bits contain the offset from the virtual address to relocate. We're only concerned with a dir64 relocation type, which is just adding the base delta to the pointer created. So explaining what this looks like, how this actually works, is actually really confusing. So if you actually look at it in code, it's actually really simple. So to get a pointer, you basically calculate the image base with the virtual address RVA plus the offset from the encoded offset. And performing the relocation is actually really simple. You just basically add a pointer delta. You add our delta to the pointer, and it actually relocates the image. So here's what that looks like in code. So you basically get the relocation table from the directory entry of the relocation directory, and then you make sure that the virtual address is not 0 for every relocation table entry. You get the relocations by basically, let me read this. Since the size of block value also contains the size of the relocation table header, we can calculate the size of the relocation array by subtracting the size of the header from the size of block value and dividing it by its base, a 16-bit integer. Okay, where were we? Okay, we're at the relocation table, and we got the virtual address. Okay, let's see. And basically, in order to get the actual the number of relocations, you have to calculate the difference between the size of the block and the actual size of the header, which is a little confusing. So you can actually just read the code. I feel like the code is actually a lot more understandable than actually trying to explain it. You can get the actual relocation data by calculating, doing some pointer math to actually get to the actual relocation data. You can see here I'm doing some funky stuff with arrays, but that basically what that line at the bottom basically does is it advances one more entry of the relocation header, which is always where the actual relocation data is going to be. So sorry if that's confusing. So for the actual number of relocations, we just basically have the encoded types, and we just basically here we just basically we get the relocation data on the relocation entry. We shift the relocation over by 12 to get the type, which is either dir64 or absolute, which is basically a no-op. And but we still need to be aware of it, and then we actually get the offset. And then basically we calculate the pointer address by calculating the offset from the image plus the actual offset given with the relocation virtual address base. And then if it's dir64, we add the pointer delta. So then we have to actually advance the relocation table, which is a little confusing because of the way this relocation works. But basically, you add the size of the block to the base of the relocation entry, and that gives you the next entry. It's like actual pointer arithmetic, but you're doing it manually. This is basically what an array does when you advance like from one block to another. Okay, we've done it. We've basically decompressed and remapped our binary for execution. We parsed and loaded the imports, and we relocated the image to point at the right addresses. Now we basically just need to transfer execution to our unpacked image. In the NT, optional headers is address of entry point, and RVA to the entry point of the given binary. We simply use a function pointer at the entry point to call our loaded image, which looks like this. You got your return type, and then your variable name is actually where your function name would be for an actual like regular function. But this is a function pointer that we're talking about here. And then you can actually add your function arguments. In our case, if you'll see the entry point cast down here with the void pointer cast, as there's no arguments. And it's just basically a void pointer. This might be relatively confusing because we're used to a main routine. But actually, the entry point for a Windows executable is untyped, so you can basically just call a void pointer to the entry point, and that'll actually basically be that'll basically and then that'll actually run your packed binary. Okay, with the entry point transferred, you're done. You've successfully packed and unpacked the Windows executable. This stuff obviously gets a lot more complicated if you've ever done malware analysis. You can see all the various tricks that malware authors tend to do with their packers. So there's a lot more to do than this very, very simple example. So some further exercises to get a good handle on packing. You can learn to support 32-bit executables. You can support other data directories, such as the TLS directory and the resource directory, which both contain their own challenges. And you can learn various anti-analysis techniques to harden your packer. I suggest looking at Peter Ferry's ultimate anti-debug uh, uh, documentation, basically. I have it linked in the README in my repo. So okay, I can open up to questions now. That's basically the end of the presentation.
First, let me just say that was amazing, and thank you so much for coming out tonight to
Thank you.
share your knowledge with all of us. I'm still soaking it all in, and I think I'm going to have to spend some time with your awesome tutorial to make sure it all makes sense.
Yeah,
Um,
it really I feel like I really explained it as verbose as possible
mhm.
with the README. It's a long read, but I think it's a well worth it.
Yeah, and the comments are excellent too. I would encourage anyone that's curious about this, like go and check out the README. I linked it in the general chat. Um, super, super informative and well done. Um, so let me just open up the chat window here. I'm just gonna like read the back scroll and see if we have any comments. And if anybody wants to like just jump in and ask a question, you can go ahead and unmute yourself and do so. It's kind of an informal thing we got here. Okay. So we have a question from Virus. How are you establishing the offset without using the PEB in the unpacker?
How am I establishing the offset without using the PEB? The offset to the I know what you're asking. Get module handle A actually gives us the let me scroll back to that. Let me see. There's it's get module handle A basically gives you to the address at runtime. Where was that? That's a bit further back. Yes. You can actually access this. Actually get module handle A basically resolves the PEB and gives us a pointer to our PE header at runtime. That's what makes adding a section so useful.
So we got a thumbs up in the chat, so I guess that answers the question. Um, Anyone else want to jump in? If you want, just like unmute yourself, no big deal, or you can drop it in here and I'll read it out for everyone. Okay. Got a question from NetSpooky asking, "What's your favorite packer?"
Um, SAF engine. SAF engine is the packer that completely defeated me when I was at Palo Alto Networks, and it was so funny. It was a Chinese packer. It was a commercial packer apparently because it was just selling on its own website, and I was debugging it, and I was working with my Chinese coworkers at the time, and basically a message popped up while I was like trying to debug it. It was like crazy. It was just ridiculous trying to deal with it. And a message popped up, and it was like a custom implementation of message box from the Windows API. So like I had no way to actually call it. So I actually called my coworker over, and he was like, I asked him like, hey, what the hell is this message saying? And he told me, oh, it says please stop debugging me. And I thought that was really entertaining. And it's the Packer that completely defeated me, and I hope one day to be able to emulate in some way because it was basically a whole lot of different stuff in there. It was really great.
So we got another question from Virus. Have you managed to implement this without the need to reread the PE from disk?
Oh, because of Git module handle A, it already has the PE header loaded into memory, so we don't actually have to read it from disk because the PE header is already loaded into memory, and the section table that we've added is already loaded in memory, so we just recall it from there. And that way we don't have to because the image everything is loaded into memory with the P with the current runtime. Um, yeah, we don't actually have to because of the way we're okay. Let me. I think I answered that part, but I think there's also another question here. How do you do this without actually dumping the executable to disk? We're basically what we're doing is we're basically resolving the loader so that we don't actually have to dump to disk, and we can actually get our executable from memory with the because it's actually loaded with the executable that we're running.
So I see a couple more people typing. We might have one or two more questions.
Okay.
And if not, I think we can call it a night. Okay, so we got a question from Remy. At the end there, you mentioned TLS data structures. I've read about the usage of TLS packers due to, I want to say, something related to loading order. Can you briefly talk about some of the attributes of utilizing TLS that make it desirable for a packer?
Yeah, absolutely. Like the TLS directory is actually really great because the TLS directory gets loaded before the entry point of the actual binary, which is why you actually have to you have to take the TLS directory into account when you're doing like when you're trying to support more executables, because you have to call the TLS directory and all the TLS directory base of entry points in order to actually successfully unpack an executable. So the TLS directory comes first, and then you call the entry point, and that's how the loader works. So the TLS directory is actually used to bypass the original entry point for a lot of analysis. So that basically, when the TLS directory gets called, if you're not careful, if you're not actually setting breakpoints on all the different TLS directories with all the different TLS entries, uh, TLS, by the way, stands for thread local storage. It's a way to basically store thread local memory within an actual executable. It actually has a legitimate purpose, but because of the way it works with the loader, it's ideal for actually ideal for basically obfuscating your actual original entry point. And you can actually do various things to the, with once you're in the TLS directory, you can do various things. Like you can basically implement anti-debug checks before the entry point for your packer, or before the entry point for your executable even gets called. It's great. I can't recall the way to do this with Visual Studio, but there is a way to actually add arbitrary TLS directory entries within Visual Studio.
We got a few more comments, or a few more people typing. Netspooky says bread local storage. That's yeah.
Thread local storage.
Yeah. Okay, so question from Ataxia. So if you put the executable as stray data not covered by the PE header, you would have to unpack the disk, right? But because you're
Yes.
adding but because you're adding a section to the executable, you don't.
Yes, exactly. You can technically concatenate data onto your executable and it'll be fine, but it won't be loaded in memory. Then you would have to read it from disk. You can basically, if you're familiar with like ping polyglots and adding arbitrary data to pings, PNG files, you can basically just concatenate data onto the end of your under the end of your executable if you want. Then you would have to actually like read and parse the actual PE file on disk. But yeah, but because we're creating a new section within the actual executable, you don't have to do that.
Cool. One more question from Virus. Have you tried implementing this with Heaven's Gate yet?
No, I haven't, but I want to. I love Heaven's Gate as an idea, but like I haven't gotten to that advanced. That's more like advanced implementation of syscall and other sorts of EDR bypassing. That'd be that's a great idea though.
Yeah, actually, now that I think about it, one of our speakers next month, I think, is going to demo Heaven's Gate and Hell's Gate
Oh,
implementations.
perfect!
So
I will have to be there for that.
yeah, I'll ping you for it. It should be fun. So I want to be respectful of your time, Frank. If we've already been going for an hour, so if you have to call it, that's fine. Thank you so much for
Yeah, I
coming
got to get
out.
started on dinner.
Yeah, I understand. So I guess we'll end the stream. I'm gonna stop the recording in a minute here. Once again, this talk was awesome. I'm so happy that you joined us. I'm really excited to
I'm happy
actually,
to be invited.
yeah, I'm excited to just sink some serious hours into your tutorial and make that happen. I'm gonna learn a lot. Um, okay, so I'm gonna
No,
end the
I love
stream.
Packers. If I can get more people to write more different Packers, that's great.
Yeah.